Hello students, in this particular video I am going to discuss one numerical from the electrochemistry chapter given in GATE 2019 question paper. Now let us go through the problem first. Now here this is the electrochemical cell that is given to us, and where M is a metal. The temperature is given as 298 Kelvin. So T is given as 298 Kelvin. Now here two reduction potentials are given. If we observe carefully, see here, this is M2 plus aqueous bar M solid. So this is M2 plus aqueous bar M solid. That means this is nothing but the reduction potential of your right hand electrode. And obviously this becomes the reduction potential of the left hand electrode. So therefore we have E0 of the left hand electrode is equal to minus 0.36 volt. And E0 of the right hand electrode is equal to minus 0.12 volt. And we know that E0 of the cell is equal to reduction potential of the right hand electrode minus reduction potential of the left hand electrode. So this is the formula for the E0 of the cell. Therefore E0 of the cell, now that becomes equal to minus 0.12 volt minus of minus 0.36 volt, that is equal to 0.36 minus 0.12 is equal to 0.24 volt. Therefore E0 of the cell is equal to 0.24 volt. And then 298 K, and here it is very clear that N is equal to 2 mole electron, and given F is equal to 1 Faraday is equal to 96,500 coulomb per mole electron, and the temperature coefficient given as dU0 cell by dt dou E0 by dou T at a constant pressure, that is equal to 1.5 into 10 to the power of minus 4 volt Kelvin inverse. And what we have to calculate is that we have to calculate the delta H0 for this particular reaction. Okay, now the formula for the delta H0 is equal to delta H0 is equal to NF into T into dou E by dou T, dou E0 by dou T at a constant pressure minus E0 of the cell. So this is the formula for the calculation of the enthalpy for the reaction. And of course we have delta H0 is equal to standard enthalpy for the reaction. So that implies delta H0 is equal to N. N is nothing but your 2 mole electron, and then Faraday is nothing but your 96,500 coulomb per mole electron. Mole electron gets cancelled. Into temperature is 298 K, and then now the dou E0 by dou T is given as 1.5 into 10 to the power of minus 4 volt per Kelvin, minus E0 is nothing but your 0.24 volt. So Kelvin gets cancelled. Now this is 2 into 96,500 coulombs, that turns out to be 2 5s are 10, 2 6 are 12 plus 1 13, 2 9s are 18 plus 1 19. So 193,000 coulombs into 298 into 1.5 into 10 to the power of minus 4 volt minus 0.24 volt. And then now if we calculate this value, 193,000 coulomb into 298 into 1.5 into 10 power minus 4 volt, that turns out to be 0.0447 volt minus 0.24 volt. Now this value is nothing but 0.24. So the value of this 0.0447 minus 0.24 is equal to minus 0.193,000 coulombs into minus 0.1953 volt. So therefore now this into 193,000, that is equal to minus, this value turns out to be minus 37,692.9 volt coulomb. We know that 1 volt coulomb is equal to joule. So this is equal to minus 37,692.9 joules, and that is equal to minus 37.692 kilojoules. Therefore the delta H0 for this particular reaction is equal to minus 37.692 kilojoules. So this is the final answer. So the standard enthalpy for this particular reaction is delta H0 is equal to minus 37.692 kilojoules. Thank you.